Hello everyone, this is Brock Skaggs, and I'm going to make this video where we'll investigate drawing the shear and bending moment diagrams for the simple supported beam you see before us. And in a previous video I used an inspection method where we came up with the reactions using a free body diagram and equilibrium equations, and then drew the diagrams first and then used some analytic geometry methods, if you will, to come up with equations for the line, and also had to do some calc in order to come up with the equation of the parabola and so forth. Well, here we're going to tackle it in a slightly different way. Our still ultimate goals are to be able to draw the diagrams and come up with the equations to describe the curves or lines or whatever that is happening on the diagrams. But here we're going to use a series of free body diagrams. And so the idea is we'll first have to determine the reactions, which I've got already done and on the screen now, and I'll let you kind of peruse that at your own will. But then we draw multiple other free body diagrams, and each free body diagram is going to expose the internal shear force and internal bending moment on some cut section that we make along the length of the beam. And from knowing that slice of the beam, if you will, or that chunk of the beam is in static equilibrium, we should be able to write our equilibrium equations and come up for expressions of the internal shear force and the internal bending moment at that given point. And so we could set a specific point when we make the cut and say exactly at 4 meters to the right of A or 9 meters to the right of A. Or we could also say, hey, let's make this a floating cut here, if you will, so we can define ranges. And so the key in defining the ranges is to make sure that you are in the right domain. And so, for instance, here, hopefully as you do these, you can kind of develop this intuition and basically be able to say, hey, there's going to be two relationships here that are going to describe the internal shear force and the internal bending moment. And so I'm going to have two different free body diagrams I'm going to have to draw after determining the reactions. One, I'll basically have a cut that passes the right-hand cut through the distributed load portion here, and it'll be anywhere between x equals 0 and x equals 8, and the other will be as soon as I get past 8, and between 8 and 12 being my right hand cut, will be another free body diagram here. Notice the free body diagram, yes, the lengths are changing, but more importantly, the loading is changing as well, which is going to cause different things to happen for the internal shear force and internal bending moment. And so again, I've already figured out the reactions a sub x, a sub y, and b sub y. Those are right down here. Found out a sub x is 0. You can see b sub y is 2,666 and 2/3 of a Newton, and a sub y is an upward reaction of 5,333 and 1/3 of a Newton there as well. And so now we're going to start hacking this beam up in certain sections. And so I'll try to illustrate this by just sketching on my image here. And so the first one will be as if I make my free body diagram cut, and let's say the boundary is the blue here. And so what I'm doing is I'm making my left-hand side cut right at the reaction here. So I get the a sub y reaction in here, but then my right-hand cut, notice I'm stopping short of the end of the distributed load here. And so we're going to have that at some point x as far as the length of this cut section, and that x is going to be between 0 and 8. And so that's exactly what I'll start doing down here. Let's draw a free body diagram now. And we're going to say that x has got to live between 0 and 8. Just like so. And so here's my cut section. Well, one thing I know is I'm going to have an a sub y reaction force pushing up. And that is equal to 5,333 and 1/3 newtons. But what happens on the top of the beam? Well, anywhere I look, I'm going to see the distributed load, right? And so there's going to be some distributed load all the way across this. In order to make things easier, we can still think of it as an equivalent point force here, but this capital W here is not going to be the 8,000 newtons that we used when we drew the free body diagram of the entire thing, because if I'm using x to float between 0 and 8, if my x is only right here, well, that's less than half of the distributed load, so there's no way it's going to be 8,000 newtons. It would be less than 4,000 where my cursor's at currently now. And so in order to help us with that, we'll just say, well, that's always going to equal the area under the distributed load curve up to that point, and so it'll just be lowercase w times x, where here I have to make sure I note that this is a distance x units away from the origin. And so what is this distance here? Well, it's a uniform distributed load, so it'll be right in the middle, and so this will be at x over 2. And so that's x over 2 from both sides here. And so that should take care of the distributed load that's going to be covering our chunk of beam here. But what happens here? Well, here's where we have a cut surface, right? We're cutting through the material of the member itself with our magic knife, if you will. And so here we think, well, there's an internal shear force and internal bending moment that could be present. And so it's somewhat important as far as how you assume these to be in positive or negative directions. But the assumption that we'll use in our class is that a positive shear force and the positive bending moment on the left-hand side of a free body diagram cut is going to look exactly like I drew it on the screen there, where positive V is actually downward and positive M is counterclockwise. I've actually got in my other notes, as far as with a different lecture, this image here, which is setting up that convention. And so here you can see we cut there, we took the left-hand side, and this will be positive V direction and positive M direction here that I've drawn, just like I drew right here. And all that does is basically make sure that we all transition correctly, or transition the same, if you will, between our internal reactions on our free body diagrams to what we're going to call positive or negative as far as above or below the x-axis on our shear and bending moment plots. And so at this point, we're ready to write some equilibrium equations. So our free body diagrams is all filled out. We've got all the reaction forces, the distributed loads taken care of, the internal shear force and bending moment around there. We know the distances between everything. And so with that, let's go ahead and write some equilibrium equations. Here, I can just go ahead and start with the equilibrium in the vertical direction, so some of the forces in the y. And I can say, well, it's plus a sub y minus capital W, or I could put minus lowercase w times x, is the way I'll write it here. And then minus v is equal to 0, because v is directed downward. And here we're using the convention here that positives upward like we usually would. And so v, I can say here, is equal to negative lowercase w times x plus a sub y. Right now everything is in variables, so let's find what lowercase w was. That was 1,000, so here v is equal to negative 1,000x plus a sub y, where our a sub y we set here was 5,333 and a third newtons. So just like so, now I've got a relationship that tells me the magnitude of the internal shear force over the first 8 meters of the beam, essentially. And so now we'll do a very similar thing for obtaining the internal bending moment. And so I'll sum the moments counterclockwise positive about point x, where here I'm really thinking point x is right there. And so the internal shear force V is right on that plane, so it doesn't enter into my equation. I've got the internal bending moment M there. Working right to left, you can see our static equivalent point force, lowercase w times x. It'll be times x over 2. It's also trying to cause counterclockwise rotation, so positive here. So plus what'll be w times x over 2. And then way off on the far left end of the beam, I've got a sub y pointing upwards. It's going to cause clockwise rotation. So that'd be negative a sub y times that horizontal distance x. So if you spend some time really clearly building your free body diagram, these equilibrium equations become easier to write. And so here, I go m, it's what? Negative w over 2 times x squared plus a sub y times x, kicking it to the other side, and filling in our values. Lowercase w is 1,000, so this is negative 500x squared. And then plus, we already know a sub y is the 5,333 and a third, and then we multiply that by x. And so this is a characterization of the bending moment as we move between 0 and 8 as well. A nice thing about this is we can check ourselves a little bit. I've talked about it before, that there's a relationship here that basically says that dm dx is equal to v. Let me go ahead and erase this, make sure nobody thinks that's an integral sign. And so if I take the derivative of this expression here for my internal bending moment with respect to x, I better get the relationship for the shear function, and that's exactly what I have. Negative 500x squared plus 5,333 and a third x. If I take the derivative of that with respect to x, I get this line right here, negative 1,000x plus 5,333 and a third. And so that's one nice little check you can have between those two quantities. So now we're, I guess, halfway done. Now we just have to do it for the last bit of the beam here. And so here we'll draw another free body diagram, except our boundary for the right hand side of the free body diagram is going to change a little bit. Last time it was between 0 and 8. Here we need to be between 8 and 12. And so I'll go back up to the picture here. Essentially what we're saying is, well, we'll keep the left hand side the exact same. We'll cut it right here from the reaction, but now it'll be our green one, and here we're going to move that and elongate our beam chunk until it gets past the end of the distributed load. So now it'll look different inherently from our first one, because there's going to be a stretch of beam that is not going to be under the distributed load, which is going to be the key for having this piecewise defined relationship being set up. And here, let's go ahead and make it black still. Alright, there is our beam. Again, we made the very far left, so we still have a sub y. But at this point, now we're cutting it past the end of the distributed load, and so we can think of having the statically equivalent point load for our distributed load be equal to the total 8,000 newtons that it's pushing down with. And so it'll be very similar to what we've done here with the free body diagram, the entire beam, to come up with our reactions. And so here we can draw it still as our capital W, but this time we're allowed to say, hey, that's the entire 8,000 newtons, because this free body diagram stretches far enough to the right to include the entire thing. And it's going to be placed at a distance of 4 meters from point A, because it has to live at the centroid of the area under the distributed load curve. And so that's why we get our 4 meters there, half of the 8, which is the overall base of it, since it's just a rectangle. After we get past the distributed load, remember there was nothing here, and so all we have left as far as forces and moments are the internal shear force and the internal bending moment. Again, drawing them in this orientation because I'm making a free body diagram cut and I'm taking the left hand side, so this is indicative of positive V and positive M directions. Other thing to make note of here is, again, I'm going to be considering X to be this point here. We'll have some overall length of this beam segment also is X units away from the far left hand of the beam, or basically where our origin is at. So after we've got it set up to this point, it's just a matter of writing equilibrium equations again. And so we'll run through this just like last time. So we got some of the force in the y. We've got positive a sub y minus our capital W minus v is equal to 0, which is very similar to what I wrote here, except for be careful of how you interpret the capital W aspect of it. And so v here is equal to what? Negative W plus a sub y. So that's negative 8,000 newtons here, plus a sub y was our 5,333 and a third newtons. And so, grabbing the calculator, negative 2,666 and 2/3. That'll be in newtons. Here I'm going to go ahead and actually leave off my units here, and I'll just talk about units at the end. So it's a constant here, which does make sense, right? Here I've got no forces acting between 8 and 12 meters, and so we'd expect this shear force to be a constant, not changing. And then for the bending moment, just like before, I'll take the sum of the moments about point x. Counterclockwise is positive. Again, the shear force basically works right in the plane that their cut is being made, so it has no perpendicular distance, if you will, so no contribution to the moment. We'd have positive m plus here. Notice the counterclockwise tendency for capital W to rotate about point x. And so that is the 8,000 newtons for the capital W times the distance. Well, the distance here isn't explicitly given, but it's this distance right here. That'd be x minus 4. And then we'd also have a sub y here on the far left. It's trying to cause clockwise rotation, so negative contribution to the moment, so negative a sub y times x. And so now solving for m. So m is equal to, you got positive a sub y times x, and then you would have what else? Negative 8,000 x plus 32,000 is just a constant here. And so a sub y was our 5,333 and change times x minus the 8,000x plus 32,000. And finally, one last step for our simplification. We got 5,333 and a third minus our 8,000 gives us the negative 2,666 and 2/3 x plus 32,000. Again, we can make the check. If I take the derivative of this expression, I do indeed get the internal shear force over the same domain, so that looks good. And there we have it in terms of coming up with our relationships. We've got between 0 and 8, 8 and 12. That's the entire length of the beam. The only thing left to really do is write those in nice piecewise defined equations. And so we could again do that quickly here. We'd have v as a function of x. Got two relationships here. X is going to be coming in meters, and v will have units of newtons. And to see if I can grab some of these values, here's our v2 as a function of x. There's that. Looks like I lost my curly brace here. So there's that. And this goes here. And then the first v as a function of x was this linear function here, which goes here. As far as domains, 0 is less than x. Remember, we've got that concentrated force happening right at the point at the start, and then that goes to less than or equal to 8, and then 8 picks up less than or equal to x, which is less than 12 here. Both of the endpoints here, we've got concentrated upward forces associated with the reactions a sub y and b sub y, so that's where I'm leaving off the less than or equal to on those. And now for the bending moment. M is a function of x here. Here x is again going to be in meters, and m will be in Newton meters. Here's the m2 as a function of x right here that we solved for. And then the m1 was the parabola here. And so relationships here, there's no concentrated moments happening, so we can put less than or equal to's on both of these sides, so it'll be between 0 and 8, and between 8 and 12 here. So at this point, I believe we have our expressions for the internal shear force and the internal bending moment here. And so just taking a brief moment to check the notes. And yes, everything is looking good at this point. One thing that is somewhat lacking in this is, hey, how do you draw the diagrams now? You basically could sketch it out if you wanted to, or the nice thing about this is we've got the equations, so you could just plug it into a computer algebra system like I'm doing here with, with Wolfram, not Wolfram, but Sage. And so here in blue is the shear force, which should be the equations that we just talked about here. I've got V1 and V2, and here is M1 and M2, and the red graph is my bending moment as a function of the position along the length of the beam. And so that's completes what we're after for this problem. One thing, I'm kind of showing two different methods at this point, an inspection method and this free body diagram method. Really both of them will get you the exact same result. It's just some of them might be quicker, or one method might favor a specific beam and loading more than another there. And so what I like to do is, of course, I learned them both, and so now I can kind of pick and choose the method depending on this problem specifics that I have there. But again, both of those roads should lead to the same final answer there. And so it's one of those personal preference things to some degree. So thank you for watching the video, and I hope this helps you with your shear force and bending moment problems.